Right. Hello, everyone. So let's get started off with introduction for our workshop today, which is Introduction to NLP with Deep Learning with TensorFlow. So today we'll be discussing what deep learning is and and how TensorFlow syntax also works. Right. So just to introduce our speakers, so Andrew's here. So Andrew is one of our speakers as well. So Andrew is a grade 11 student at Saint Albert Secondary School, and he's the co-director of Ignition Hacks. He's a deep learning practitioner who's proficient in TensorFlow, Keras, and PyTorch. He was placed 29th in the world on the Kaggle Kidney Segmentation Challenge, and he's also started his own summer company called Shawbotics. You guys can check out Shawbotics, and you can also connect with Andrew on Instagram with this Instagram link here. Alright. So moving on. So hi guys, my name is Gagan Bhatia. I'm a fourth year computer engineering student at UBC. Currently I'm interning at AWS CIC. And in the past, I was an ML research assistant at QCRI, which is the Qatar Computing Research Institute. And in my free time, I also work as a mental health advocate. You can go ahead and scan the QR code from my LinkedIn, and you can also or you can also go to visit this website, which is linkedin.n//g 30 at link, which is my LinkedIn username. All right, so nice to meet you and nice to meet everyone here. And so since we're live here, so I'm just going to be going through what deep learning is, what NLP is, and what and how the TensorFlow format works as well. And along with that, I'll also be explaining what transfer learning is and how the transformers work as well. And at the end, we have a fantastic move built by me and Andrew. And then the demo will be actually showing how NER works, or NER, or natural entity recognition works as well. Looking at the agenda for today. So today, first of all, we'll be going through what deep learning and neural networks are, and secondly, we'll also be going through how the TensorFlow syntax works. And after that, we'll be going through what transformers and how Hugging Face works. Along with that, we'll also be discussing what pre-trained and transfer learning is. And finally, we'll be going through the Collab notebook, which focuses on NER. So it's going to be a really interesting journey, and I really hope that everyone can learn something from it. And if you guys have any questions, you can always put it in the you can always go to the Slido chat and you can put the comments there, and I'll be monitoring that. And if you have any other comments, you can also use the YouTube. And if you're watching on YouTube, you can also use the YouTube comment section as well. All right. So if everyone's ready, let's get started. So let's get started. So let's talk about what neural networks and what deep learning is with TensorFlow. Before we actually talk about what deep learning is, let's actually first look at the interesting part, or the applications of deep learning. So there are multiple applications of deep learning, and then the most common ones are in computer vision, natural language processing, and audio and sound manipulation. So firstly, how it works for computer vision is that we actually allow the computers to see, on which is basically we're using image classification, image segmentation, and object detection. A lot of us might have actually seen those images with boxes around a person, and that are being used to train a different kind of computer vision models. Computer vision is actually one of the most powerful users of deep learning. Along with that, today we'll be focusing on NLP, which is natural language processing. NLP personally is my forte, and I've worked a lot of different NLP models and done a lot of different NLP research things as well. And NLP basically converts language or text to computer to machine language as well. It basically helps machine to understand and create and manipulate language. So basically, like how we can understand English or any other different languages. So NLP allows the machines to also understand these different languages and actually perform different tasks based on them. Like good examples of tasks would be like text classification, or which is an example of sentiment analysis and token classification, and so on. We also do have question answering, so you can give it a paragraph and ask a question, and the model will generate an answer for it. And finally, the topic that we'll also be covering in our demo today, which is natural entity recognition. I'll be going through in more detail what NER is in the coming slides. But for now, it's really important to know that NER is also one of the most very powerful NLP resources. And finally, coming to audio classification, and sound event detection. Or actually manipulating audio and sound actually can take up a lot of intense resources as well. And deep learning is quite resource intensive in itself as well, because all of these tasks like computer vision, NLP, and audio usually require a large data set to train a model as well. And whenever we actually do use a trained model as well, just predicting from these models can be very impute. So it can be very intensive to help from compute as well. So it's actually quite important that we make sure that we are that our text classification and our audio and all of our models are working well. Looking at so actually focusing on what the artificial intelligence landscape looks like. So deep learning is so if you actually just look at the diagram here. So deep learning is actually a smaller part of what machine learning is, and in itself, machine learning is a small part what artificial intelligence it is in itself. So as we can see here, so there are three different layers. There's machine learning, deep learning, and we also have artificial intelligence. So as we can observe here, these are three different things. So as we can see, deep learning builds on what machine learning has been done, and artificial and so on and so on the relationship with artificial learning as well. So all of these are different the AI algorithms that we've been using for different tasks that we can actually fine tune and we can pre-train our models for. And one really interesting thing that we'll be covering today is unsupervised learning. So one of the most common unsupervised learning is clustering. As we can see here, there are different clusters of data. So all of these data have been clustered according to a certain rule that has been applied in this case here. So all using this rule here, we can actually see what the cluster data is and how clustering works as well. In unsupervised learning, there is no validation. There is validation, of course, but there is no supervision from a person who's actually monitoring these data sets. And finally, coming to what is deep learning. Deep learning is complexified and powerful machine learning, or whenever we have three or more layers, that can be called deep learning. So let's actually take a look at the deep learning process and how deep learning actually works. So deep learning is actually quite interesting, and I find deep learning really interesting, and I've worked a lot with these deep learning algorithms, and it's quite interesting to understand how these things actually work here. So how the deep learning process works is that we actually first of all we make a guess, and actually evaluate like using a high parameter model, and we trying to make a guess on what the prediction could be. And secondly, so we are so using the deep learning process. First now that we have actually evaluated it, now that we actually used a prediction, or we have actually made a guess using a very high parameter model. So we actually first of all we make the prediction. Now, secondly, then we actually evaluate that guess, that how correct that guess is using a cost function, or is it like and also we can also use a cost function to reward how poor the guess is, and we can use a reward function to like how good the guess is, and it's quite similar to how reinforcement learning works as well. And so if you guys have actually worked with the reinforcement learning, it's quite similar to that as well. And now that we actually see, so now that we actually have a cost function, reward function, or basically now we understand that how good our guess was or how bad our guess was, we can use the data to actually improve the model. And so improving using so there are two different ways to improve the model here. Firstly, we can use a gradient descent, and there are multiple types of gradient descents that can actually be used in this case here. Secondly, we also can use an optimizer that will reduce the loss or increase the award, and so on we can actually increase the loss, and so on we can actually tune the model to make sure that our deep learning model is working correctly and our deep learning pipeline is working as smoothly as possible. It's quite important that we actually follow this process and make sure that our model is performing accurately. In this case, deep learning models usually end up having a higher accuracy level than any other machine learning models, and it is because of this process that actually makes the deep learning models more and more accurate. And so let's actually look at what basic natural language processing looks like. So as you can see, this is quite similar to what a convolutional neural network looks like. And this is just looking at an like NLP classifier. We actually so firstly whatever we do, so we actually so one of the major starting points of any natural language processing task is the language part, or basically it's just text. So we actually, so first thing that we need to do, and again, machines cannot really understand text like the way we do. We have to break it down, or we have to convert it into embeddings, so that the machine can actually understand what is the text about, and what are we talking about here. So the first thing that we need to do is to take in the input cell and convert it to an embedding. And every neuron here is connected to a different hidden cell. As we can see, so we have just three inputs, and we have four hidden layers here that connected to output scores. So how it actually works is, so we actually take each neuron. So first, now that we have converted all the text to embeddings, and we connected to file class, every neuron is connected to the neuron before here, and every neuron is also connected to a hidden layer in this case. So using a softmax function, we actually get an output score of what or output score or an accuracy score depending on which class it is. So if you actually look at a multi-class classifier, using this algorithm, we can actually see that which class would it belong to. So maybe if you're actually looking, maybe let's say if you're looking at sentiment analysis, and we have like three classes, we have like positive, negative, and neutral. We can actually use the softmax function to predict an output score of what class would the text belong to, with what probability as well. And that is how an MLP classifier would work here. But in most of the deep learning ones, we actually use LSTM, or which is long-term short-term memory processing, or which basis. And how an LSTM works is, so how it actually works is, so this is a really good example of how an LSTM works. Here we have an LSTM unit which takes an input which is xt, and processes it one by one. So here we take in xt, and then we go through our LSTM unit, and it keeps a long term, and it also keeps a short term memory state. So it can remember what the previous words were. It can also remember what the long term, like the long term short memory were as well. So that actually gives us an advantage here. And then using that, we can also, so here we have multiple hidden layers inside an LSTM cell. So using those different layers, and one LSTM unit is attached to different LSTM units as well, which are performing processing for xt minus one and xt plus one as well, and so on. We actually get these and so using the and now that we actually start processing it here, using the different algorithms that we have applied in this case, we would actually focus, and we would get a results in form of an OT, which is basically our output here. And so on we can, and this is basically how an LSTM cell would work in this case. Now that we actually gone through the theory, let's actually move on. And I've actually been going through the theory really quickly because I'm sure everyone's more interested in how can we actually implement TensorFlow, and how can we actually use TensorFlow in this case here. So let's actually look into what the TensorFlow basics are, and how can we actually build an LSTM model. And one of the really cool things is that we'll be using our same LSTM model to be, so that we can train it, and we can use this. You can use a model here in this case to train it to use an NER system as well. So actually go ahead and look at what the TensorFlow model looks like. First let me explain what TensorFlow is. So TensorFlow is a deep learning library which is built by Google, and which is based in Python, that make creating neural networks really simple. So now that we're actually going to look at the TensorFlow syntax, it's really easy and really simple to understand as well. And we can also see that the TensorFlow. So let's actually go ahead and look at the TensorFlow data processing part. And TensorFlow is actually really simple to use here, and it becomes really easy to use. And the data processing and the data file, like the data cleaning up, becomes really easy to use with TensorFlow. And now that we're just explaining the syntax, I think we'll also get a chance to actually explain how the code works as well in our actual workshop demo. So so everyone just stay tuned for that. We'll get there as well. So firstly, as we are starting off for data processing, the first thing that we actually use is TF data, or which is basically the main model for TensorFlow data processing. And as in every NLP pipeline, we also need to use a tokenizer. As I mentioned before, so we need to actually convert from text to actually language the machine can also understand. So for that, we need to use a tokenizer. And we'll see once we've actually done using a tokenizer, it basically converts text to indices. And once we're actually done converting a tokenizer, we can also use data. So there are multiple ways how we can actually get the data set. So we can use the data from tensor slices, and which is also the easiest way to create a data set, which is easiest way to create a TensorFlow data set here. And now once we actually do have a really large data set, and we wanna apply like the same batch processing thing. So now let's say that we wanna clean up the data, and we wanna apply the same function to every row in the data set. So how can we do that? So it's quite actually, so I mean, for anyone who's done programming, everyone might be thinking we can use like a large for loop and stuff. But again, that's very intensive, and that can be very compute intensive as well. So what we can actually do is that we can use dataset.map, which maps a function to every element of the data set. And that makes our job really easy, and also uses TQM, so we can also monitor our progress, and we can also see how far, like what how far how far along are we in the data set. And finally, now that we are actually applied and cleaned our data set, we just need to batch our data set and create different batches out of it, so that we're not just feeding our data we just so that we're not feeding a huge data set into our model, and then it's going in slowly as well, so that we can also accommodate for any of the changes that we want to do. And so now that we actually completed the data, like the data pre-processing, we will actually want to create the different neural network models. So neural network models in TensorFlow actually is done using Keras. Keras is a TensorFlow extension which makes making neural network models really simple. So let's look at how can we actually build a LSTM model using Keras. So all of these ones are actually different LSTM and different LSTM users. And we can actually, let's go ahead and look at the syntax in this case. So the first thing that actually use is that as the tf.keras.layers, which contains the model of TensorFlow layers. There are multiple different types of layers. There's actually the softmax. There are different LSTM ones. There's GRU. There are different layers that we can actually use in this case as well. And but here we specifically be focusing on the Keras sequential neural network method, in which case we basically create a neural network in which goes sequentially, or which basically follows the same order or the same sequence that we define it to be. And using that exact list of layers is basically how our model is being created. And this is a really good tool guide that we'll be actually sharing. So the first thing that we actually just use is the layers, and just moving on from the layers, we actually want to use the sequential model here. So using the sequential model framework, we'd actually, the first thing, as I've said before, is that we have already tokenized the data using in our data processing part. Now from that text, we've already received the indices from there. But we can't really process indices because can be difficult to understand as well. So we would want to embed those like indices and convert those indices into vectors. And now vectors are really easy to process, as we've seen in the LSTM cell. Here each of these are vectors, and using n in our LSTM cell, we can easily process any of the any of the vectors that we have provided here. So using these vectors, we can actually process it and take it through our LSTM cell to get different outputs in the same vector format. And so now that we actually see, so coming now that we have embedded our layer, so we take it through our LSTM one. So using LSTM in Keras is really simple, and it's just tf.tf, which is TensorFlow, TensorFlow.keras.layers.lstm, and it's that easy to actually just go ahead and create an LSTM layer. Now that we have actually created an LSTM layer, we would actually also want to get like the final output scores. And to get the final output scores, we can just use a time distributed layer, which would be based on the same which would be based on a Keras dense layer, and we can use that layer actually to create an output score that would allow us to actually join that would allow us to output a final score as well. And finally, so that's how just putting it all together we can get and build an LSTM model. And finally, so now that we actually created a model, so here we have actually used a sequential model, and we've converted from text to indices to vectors. Then we have processed the and then we process from the vectors using an LSTM model into to get a different vector. And now using a time distributed layer, we finally got the output scores as well. And now that we have actually created our model, we would want to compile a model. So now that we have created, like, so if you actually look at it like a black box in this case, let's just for an example, we can see that now we actually assembled the box inside, and now we would want to wrap it around so that we wrap it around using using a loss and a cost function, so that we can actually run and train our model as well. So now let's see. So now actually we can use model.compile. Model.compile basically compiles the model with a loss and a cost function and using an optimization function. Now there are multiple different types of loss, cost, and optimization functions that we can implement here, and all of them can give us different outputs and different feedbacks as well. And finally we also do have model.fit. The model.fit actually takes in, so we've already processed the data, we have our data sets ready, we have a model ready, and we have already compiled a model as well. So what model.fit is basically the last stage in training any of the models that we have here. What how model.fit works is that model.fit actually allows us to train the model with the particular data set. So let's say we already have an X and a Y data set that has already been given. We have already split it into training and test data sets, and and all we have to do is just call the model and just call the data set here, and we are ready. And that's all we need to do to train a model in this case. So it's quite simple, and it's quite easy to use, and easy to use here as well. And it's just because of that the Keras makes our life really easy to actually train and build these LSTM models, as we'll be actually explaining it in the NER workshop as well. All right. So before I actually move on to the second part of the workshop, I just want to ask if are there any questions or any comments that anyone would like to share? All right. Yeah. So I'm gonna move on. Since there are no questions, but if you guys have any questions, you can always put in them in the chat, and it can help you. I can help you through it. So let's now actually look at a really interesting topic as well about what is transfer learning and what are transformers as well. And transfer learning is actually is actually really cool, and I find it really impressive as well. Because transfer learning has taken LNP to a completely different level. Because the models that actually use transformers and transfer learning usually have a very high accuracy compared to the models that use LSTM or basic LSTM cells. So let's actually look at before we actually go on and actually talk about what transfer learning is. I think it's really important to explore and understand the topic of attention. And so let's say we suppose we have these four different entities, which is like a hugging face, a hard eyes emoji, a tick emoji, and a star. So now, if you actually just want to actually get the attention of, and let's so before we actually talk about what is attention here, so attention is basically given, and each entity is represented by three vectors here, which is a query vector, a key vector, and a value vector. So all of these, as we can see here, in all of these vectors are actually provided here, and so we have the query vector which is q, we have the key vector which is k, and we also have the value vector which is v. Now, all three of these ones are actually provided into a multi-head attention. So how attention actually works is, so attention actually allows us, so in an RNN cell or in an LSTM cell, we basically can just look back one way. We can, since we're just using LSTM cell, we can actually look back. We can actually look back and actually go ahead and actually understand how the cell is actually working. But in this case, we are actually want to actually focus on a larger text and actually get more data and get more data as well. So that is why we can use attention here, and attention is actually given by the formula, which is attention using the query vector, the key vector, and the value vector is given by the softmax of the query vector and the transpose of the key vector divided by a constant, multiplied by the value vector. And as we can just visualize it from here, so we basically apply them like matrix multiplication for q and k. Then we scale it to a constant and apply the softmax function, and then we finally multiply it with the matrix multiplication. So why do we even care about attention? Because attention has actually changed and actually implemented the transformers model. And one of the most one of the most popular and most important papers in NLP is a paper which is by attention is all you need. You can find, so you can just Google attention is all you need and get all the citations and stuff. But attention is all you need has basically revolutionized how the way we actually interact, and then the way we actually use NLP nowadays. And attention is all you need actually presented this model, which is basically the modern transformers model that we use nowadays. So in the modern transformers model, we actually have inputs and outputs as well. So here we have different kinds of, we have positional encodings, we have multi-head attention model, we have a feed-forward model, and then we finally do have a masked multi-head attention model as well. So all of these different cells are actually come rise from the formula from just using attention at the basic level. And as we can see, each entity and the attention of each entity would just be given by the same formula. Just using the attention which we have actually been applying here, we actually use a multi-head attention model, a cell here. So now that now that we actually obtained the attention of one of these entities here, we would want to like obtain the attention of all of these ones on each of them. So if you would want to, so here that we have calculated the attention of Hugging Face on the again on the three different ones. What if you want to calculate the attention of Heart Eyes emoji on the other three ones? So to do that, we actually calculate them separately and we get the scale dot product attention here, which is basically the dot product of attention of all of these ones. So and the next, in the multi-head one, we would concat all of these different layers to create one linear layer, take it through a linear layer, and finally get a multi-head attention output, which is basically being used in all of these different cells here. And this type of model has actually been really powerful and can actually make a model really powerful and can be used in multiple different ways here as well. So there are different concepts that have actually been applied here. So other than attention as well, we actually do see that not just attention, we also do have positional encoding, and we also do have like input embeddings as well. And so finally, what we actually here one thing that's really interesting to note here is that we also take in output embeddings. So we do have the inputs and we do have the outputs, which are basically the output probabilities here. So we take in the outputs and the inputs as well, but the outputs are shifted right, and so basically the vector has been changed, or the output probability in the output vectors has been modified and has been shifted right. And so once we do that, so we take in the output and the input embeddings, and we take it through a positional encoding to make sure that all of the models and all the model is running smoothly, and our architecture is satisfied. So here, since we have two different layers here, we can actually use these different layers and just use the multi-head attention model here. And as we can see, as I've explained before, using the scale dot product of the attention here, we can concat that layer and get a particular multi-head attention value here. And using the same value, this is basically how the transformers model basically works. So the transform models actually allow us to use multi-head attention, and which basically allows us to operate more parallelly and get actually inject more data into the model here as well. And because of all these details, transformers are actually very heavy and can take up a lot of resources as well. But transformers actually implement allow us to use parallelism. With using transformers, we can actually really convert, and we can also, so this is a really simple example of how translation would work. So let's say we actually have a text in French, and then when we take it through our encoder and a decoder model. And the encoder model also uses, or encoder model would use all the same similar transformer model as well, and so would the decoder model. And using a simple encoder and decoder model, we can just implement the same model and get an output which is I am a student. And again, I'm not really good with French, but I think so. It's quite simple to understand in this case, though. And I think the biggest advantage here is that there's no data loss and there's no data vanishing here as well, which actually allows us to actually use more and more data and train a bigger model as well. And as I've said before, all of these models which are transformer based or transfer learning based usually end up having an accuracy which is far greater than any of the other model which is based on LSTM or any of the different kinds of cells. But one of the biggest disadvantages I've said before as well of that that transformers require a lot of memory as well. And transformers are typically are pretty big models as well. So a usual transformer like a bird or any other like bird or GPT or any of these ones are usually around 200 to 300 megabytes of data, which can be pretty intensive on a local system. And to train any of these models, we also do need a GPU instance. It's quite hard to train transformers on a CPU, and because they do, and I think that's also that. And I think one of the biggest advantages, again coming back to it, is that transformers can actually take use of GPU instances. So that GPU using a GPU instance or a TPU instance can really speed up how a transformer training works, and it can actually really superpower as well and make a training go really fast as well. And so, looking at what is transfer learning. So, transfer learning is really interesting here because transfer learning is a machine learning method where a model is developed for a task. Model which has been already been developed is being used as starting point for a model on a second task. So, let's say we actually have. I think this is a really good example. But let's say we actually have like a Lego tower, and we already built it for a particular design. But now we actually want to reuse it and build something on top of it or build something similar to it. So all we need to do is we need to train it on we need to add a data set or basically more Lego blocks, and we can just build on the same Lego base that we built before. And that is what transfer learning is basically. The transfer learning is basically a machine learning method where the model developed for a task is being reused as a starting point for a model on a second task. So if we look at an example, or if we actually look at a more detailed example here, so how traditional machine learning works is that we have a focused task and we use a data set to train our model to get our model to actually just do that particular task. And that is basically how. So maybe let's actually just look at if we just are actually just going to focus on a sentiment analysis model here, and we can just actually look at the learning system in this case, and just looking at the learning system here. So we're just going to be using in the focused one here. Now once we have actually trained the model here, and we can just go ahead and just use the learn we can just go ahead and just use it for prediction here. But in this case the model will not be so accurate because we just trained a model on a very limited data set here. But if you actually look at, but if you move away and look at how transfer learning works, is that we have a huge data set and we've already trained the data set on a model, and now just using a smaller task or a target data set, and we can just fine tune our model using the target data set to get even better results. So instead of having to train our model every single time, we can also use and we can also just continue and just training our model as well. And that is how transfer learning would work here. And let's actually look at why transfer learning is really important in NLP. And so for actually how we actually use transfer learning in NLP is that we focus and we learn on one general task, and then we transfer it to a more specific task in this case. So let's actually look at, so initially when we have like a very large data set, and data sets that are usually being trained are usually like 100 gigabytes or even 1 terabyte as well. So these are really large terabyte. These are really large model data sets as well. And finally we've also developed a model. So we have like word to vec club, bird, GPT, T5 bar. All of these are really big models and have been trained on a large data set. So firstly, what we need to do is that we need to perform pre-training on these models. And what pre-training is that basically we just take a model which is which is basically a base model, and we train it on a large data set. So now this training on a large data set is an extremely computationally intensive step. It usually requires a very high GPU instance, and it often takes really really long to train as well. And that is partially because all of these models, like GPT, BERT, T5, usually have a very large number of parameter. Particularly so, if you guys actually go in and look at GPT-3 has almost 175 billion parameters that it actually uses, and because of which GPT-3 is one of the most powerful most powerful ML and NLP models at the moment, and it is really intense. It is really fast as well. But using these models out of the box aren't enough actually for us. So since just using these models is not quite easy for everyone as well, but we actually do want to use these models for particular tasks that we want to adopt them for. So let's say we actually just want to build like a question answering system where we provide the model a paragraph, and we also give it a question, and we actually want to get the answer from the paragraph. And now, how can we do it? So now let's say that we have already built a model and we already have a pre-trained model that has been trained on a really large data set. But the catch here is that the model has not been actually been trained for a question answering data set. It has just been trained on a very generic data set. So like a pre-trained model would not perform really well on a specific task like question answering or anything like that. But we can actually use the pre-trained model. And so now that we take the pre-trained model, we can and now we now also let's say we also have a smaller data set which is more focused on a question answering data set. So using the question answering data set, we can just take up a pre-trained model and we can fine tune our model on the new data set. So just using the find user and find we can fine tune it and we can adapt it to a different data set, and to get and so we can also use, so depending on what data set we have, we can create different tasks and we can use it in different ways as well. This actually makes pre-trained models really powerful because we can adapt it for different tasks and use it in a different ways as well. And that is why we have a lot of different tasks and we can create new models very quickly as well. And let's actually look at how how language model pre-training looks like, and how can we actually do it as well. So let's say that we have like a small snippet of text here, and which is just a really simple one, of which is basically my house dash small. So there can be like different things that can come in this case. And let's look at the second one as well, and which is I love my dash. Now these are different masks and these are different dashes that we actually want to predict the word for in this case. So how prediction would actually work is that we would take the probability of this text and we would take the probability in this text, or we would also take the probability of the text or the other text, and we would actually combine them to get and predict the rest actual value here. The biggest advantage of actually using language model pre-training is that it does not require human annotation. For any of these large-scale tasks, it usually requires the human to annotate all of these values and actually get the answer as well. But since we're actually using unsupervised deep learning here, we don't really need to it does not really require any human annotation. And on the only thing that we do need and like for pre-training is to have a large corpus of data set. So whenever we do have like a really large data set that we can use and that we can implement here, we can just go ahead and build a very generic task and a very generic model that actually performs pretty well on any task that we can use, but is not good enough, and that needs to be fine-tuned or pre-trained or fine-tuned for any other task that we would want to implement. So basically, a pre-trained model is like a box that is good at everything but isn't actually really good at anything in particular. But we can fine tune it using a different data set to actually make it better at a particular task as well. So let's look at BERT. BERT are basically bidirectional transformers. BERT are one of the most powerful models out there, and you can also check out the citations that have been added in the notes in the presentation as well. And I'll also add them in the comments if anyone's interested. And how BERT actually works is that so here, let's actually just look at an example here. So here, our example is quite simple. So our example is my sheep masks are good. So here we just been given a random sentence here, which is a training input. Now that we've been given, so just using the same model, the same pipeline, and the same thing that we actually did in the TensorFlow syntax as well. We have to take it through our input embeddings. We actually have hidden states involved in as well, and then we finally have a transform model, and then we also do have hidden output states, and finally we get to get the like use just using the output embeddings, we get our answer. But what is the major difference here is that here we just using a very generic transformers model. And as I've already explained how the transformers actually work, just using the same transformers model, we can also implement the similar design that we have already been shown here. And one of the biggest advantages of using BERT is that we can adapt it to different downstream stars, as I've already mentioned. So here we just have the same BERT. So this is the same model that can be used for sentence pair classification using different data sets. So just using so if you have two data sets and you want to actually identify what are these ones, and so if we can actually just focus on these things, we can just actually focus on this and we can go ahead as well. And looking at, so if we actually look at single sentence classification tasks as well. So there are different ways, just using a different data set, we can actually fine tune BERT to actually work as a single sentence classification task as well. Similarly, if we change our data set and we would want to implement a question answering task, we can use the score data set and get an output of that. And finally, if you just want to implement like a single sentence tagging task, or which is NER, and we can use a different we can use the data set here as well, and we can also get the details here as well. So basically, adoption of new tasks is like building new towers with Lego. As I mentioned before, transfer learning allows us to use a pre-trained based model and build a new model out of it as well. And that is how you can actually use adoption, and that is how we can actually build new models and build a pre-trained model as well. So now let's actually look at the transformer Hugging Face transformer library. I'm actually gonna go through all these details first, and then we'll get a chance to answer all the questions that have come up. And just looking at the Hugging Face Transformers library, Hugging Face is actually has built a really really nice interface to use all the different transformers and all the different data sets as well. So Hugging Face is actually being, and then Hugging Face is a startup that have actually built all these different open source tools. Their slogan is that they're democratizing NLP. They've built and developed different tools for transfer learning in NLP as well. And one of the biggest advantages of using the transformer library is that it's just one line command code that allows us to use any model that we would need. And all of these models that have been actually built by research scientists have actually taken time, and they're like huge models. But Hugging Face actually allows us to use these models in a really simple manner. Like transformers also do support PyTorch, TensorFlow, and JAX, which are basically all the big machine learning models as well. And so using transformers makes our life really easy to actually implement NLP here as well. And looking at focus at the transformers library. So transformers library is a library which is dedicated to support the transformer based architecture, and it also facilitates the distribution of pre-trained models. So how the transformer library actually works is that it provides us multiple pre-trained models that we can actually use in a centralized model hub. So as we can see here, just by using the transformers library, we just have to import a tokenizer and we import the model as well. And all we need to do is that we need to define the model name, we just need to define the model name, and just we can get the model down when we can download the model in that case. And that is basically how the transformer library works here. Just using the transformer library is quite simple, and it's also part of the transformers library as well. And we do have a transformers pipeline which uses the transformers library, the data sets, the metrics, and everything that is involved. Now that we already downloaded the data set, the next thing that like sorry, now that we already downloaded the model, we also would need to actually first tokenize the data set. As I've said before, we need to convert the text to a text and embedding so that the machine can understand it. And usually the tokenization actually takes a while, because it's a really long process. But using the Hugging Face tokenized library, it makes it really easy and ultra fast as well. And we basically can encode 1 GB in less than 20 seconds, and it supports the BPP, byte level BPP, word piece, sentence piece, and all of the different kinds of embeddings. And you can always go ahead and check out Hugging Face on GitHub, the Hugging Face Transformers link as well. And finally, looking at one of the most impressive dataset library, which is the Hugging Face datasets library. So the Hugging Face datasets library actually allows us to actually go beyond tokenization and actually use the model and fine tune the model just using any dataset that we would want to. So Hugging Face datasets library is extremely lightweight, and it just downloads the dataset that we would want to use here. And as you can see here, downloading the dataset is quite simple. It's as simple as just calling the dataset and then just using the function load dataset and with the dataset name. And that's it. And that allows us, and that completely downloads the dataset onto a local system. And one of the biggest advantages of actually using the datasets library is that it also caches the dataset onto your local system, which makes it really easy to actually use the dataset again and again. And so finally, looking at the final full Hugging Face pipeline, we have the data set, which is basically the data, and we take it through a tokenizer and we complete the tokenization process. And then we also have a prediction model where we do the prediction, and then we using the model which has been downloaded from transformers, and then we can finally evaluate our prediction using the different metrics that are also available in the dataset library. One of the easiest ways of using a downstream task on a pipeline would just be to use a pipeline function here. So here, let's say that we've already so here and the pipeline function also comes from the transformers library. So here, we just want to use a downstream task, which is summarization. So we just want to summarize a really short sentence, which is an apple a day keeps the doctor away, and we just want like a five, and we would want to specify the length as well. So just using the entire, so this would actually just call the entire pipeline. So this would take the data set, tokenize it, download the model, and then actually take the model and evaluate it as well. So it's quite easy and it's quite intuitive to use these models and these libraries as well. And I think, as I mentioned before, we also will be going into and talking about what NER is as well. So, I think it's really important to like actually talk about what NER is and like how NER works before we get into the demo. And before I let my workshop co-lead take over with the demo. So what NER is that an NER is actually called entity identification or entity extraction is a NLP technique that can automatically identify named entities in a text and classify them in predefined categories. So here, as we can see, that we have a sentence which is ousted WeWork founder Adam Newman lists his Manhattan penthouse for 37.5 million. Here we can identify that WeWork is an organization, Adam Newman is a person, Manhattan is a location, and we also do have a momentary value. So this is basically how NER works. And as we see in our different demos, we'll be using NER, and we'll be using LSTM models, and we'll also be using transformers to build two different NER models, and then we can evaluate them on our different metrics as well. All right. So I'm gonna let my co workshop lead and you take over for building our NER system with TensorFlow, Hugging Face, and transformers.
Yep, so just before we dive right into the demo, let's go ahead and answer a few of the questions that you guys have posted inside the chat. So the first one was, what is an LSTM? So when Gigan was introducing kind of the idea of an LSTM, you have to understand that humans like to build deep learning systems based on how we act as, let's just say, a human. And so how the LSTM was created was really that humans saw that we like to read from left to right. And basically, they took that idea and ran with the wind. So, how an LSTM basically works is that just like how a human might read the sentence, let's just say basic natural language processing, you might first read the word basic, and knowing that context, you would then read natural language and processing, and therefore you'd understand the entire sentence. And LSTM works kind of like that by taking in, let's just say, first the word basic as xt minus 1, processing it, and then storing that inside of some sort of kind of like history. And so by doing that, it can keep kind of some of the ideas of context as it moves on to the next words, including natural, language, and processing, effectively allowing it to slowly read in sentences, just like how a human would, left to right. Now, we've kind of modified that classic idea of how humans operate with reading with something called the bidirectional LSTM. And the idea is that you kind of need context that is both left to right and right to left in order to read a sentence effectively, just like how a human might read in small windows. And so, how we've achieved that with bidirectional LSTMs is that we have one LSTM just running left to right. So, for instance, it would first read the word basic, natural, language, processing, and then it would make a decision, versus a second one that would also grab some information from right to left. And so it would first read the word processing and go backwards. And so by combining those two, we can kind of gain some intuition from both sides of context. So the idea behind the LSTM, or it's called long short term memory, is that we're able to process in words sort of like how a human would actually go about reading them left to right, and storing in kind of the values as you're going along. Does that make sense? All right. The next question was the idea of what was generalized attention and kind of what was the math behind it. So, similar to the LSTM, attention was based on the idea that humans would focus on certain words and focus on and put more weight on certain words compared to others when they're reading a sentence. For instance, let's just say, let's take the title, let's begin with generalized attention. When you go about reading this sentence, you would probably focus on a few key words, including generalized attention and maybe the word begin. Other words that are kind of not as important, like let's and with, you might kind of ignore, you might hide. And so we kind of use these three vectors that might have caused a little bit of confusion. They're called the query, key, and value vector. And so they allow us to basically compute what is called attention, allowing us to focus on certain words over the other. So the simplest way to explain these three vectors and what they really mean is that the query vector is kind of what are we looking up. And so now we kind of give the meaning behind the query, key, and value vectors based on their names, but in reality, we're kind of training the model, hoping that it'll learn these things. So the query vector was intended to kind of look up certain things that the model would need. The key value would kind of match a query to a key, and then the value vector would give it some information along with it. And so by leveraging those three kinds of aspects of information retrieval, we can focus on certain words, let's just say the word begin, generalized, and attention, and allow our model to focus on those keywords compared to reading in everything and keeping in everything as an LSTM would. And so that has allowed us to get higher than LSTM performance by forcing our models to kind of focus on certain words that have a lot more weight. And when it comes to classification, leveraging those specific words to make its decision. I'm hoping that makes sense. Okay. So in terms of are we implementing anything with code? Yes, for sure. So once we get done explaining the rest of these questions, I will dive right into our demo, which is a Google Colab notebook on building LSTMs and transformers using TensorFlow. So that'll be at the end. And so the final question is, how can I use BERT for information retrieval? And so by leveraging kind of BERT, this is called kind of like extracting features. So if you notice, our BERT model is really just a bunch of layers of these kinds of transformer blocks in attention. And so as we slowly refine down, let's just say from our raw words, and we stack on more and more layers, we can extract better and better features from the words. And so if we can only keep the most salient of features or the most important of features using our BERT model, we can kind of train our model to focus on only the most important details for, let's just say, classification or natural language or natural entity recognition or stuff like that. Or I think it's named entity recognition, but basically just pre-training on a task and only grabbing out the base layers, because those will learn general information. So just like how Gagan was explaining a bit about transfer learning and pre-training, we can kind of use BERT for extracting out features and grabbing out more information by leveraging the fact that it will focus on the most important words for, let's just say, classification, and that will kind of slowly refine down the information as it's getting processed down. So by leveraging our BERT model, we can extract the most important of details, allowing us to learn more about our data and ultimately grab the most salient features using our BERT model by pre-training it. Does that make sense? All right, perfect. So let me go ahead and change the screen, and then we can dive right into the demo. So our rough demo will look like, we'll first train an LSTM using TensorFlow, just to demonstrate kind of like the most basics of syntax and get a rough introduction into kind of raw TensorFlow. And then we'll dive right into kind of processing everything with Hugging Face, transformers, and really leveraging that kind of powerful pre-training. So for everybody who needs it, the link I will post inside the hop-in chat, unless it's already there. Oh, it's already there. Okay, perfect. So everybody has access to this notebook, and this is called a Jupyter environment. So for anybody who is unaware, Jupyter is a Python basically notebook, allowing us to run code cells rather than your classic script. And so the reason why we're leveraging Colab today is because Google Colab allows us to gain access to, let's just say, free GPUs and free resources in general. So I'm sure everybody at this point has heard of like GPUs and CPUs. Basically, GPUs are canonically used for gaming, but they're also very, very important for deep learning because they can process kind of rapid, let's just say, computation really, really quickly. So it allows us to train our models a lot faster. So if you need to activate a GPU, you would click on this RAM button, and you can simply press change runtime type and go ahead and click GPU compared to none. And after you've done that, you will gain access to a new GPU runtime. Now, in terms of processing all of this data in, I've already done a little bit of it for you because it takes a little bit of time. As you can see, it took 2 minutes. But basically, I've extracted the data from a Google Drive link, and I've loaded in some basic TensorFlow, like just some basic data science imports. So our first major code cell is right here. This is how we go ahead and actually load in TensorFlow and some other handy data science imports that we're going to need in basically every data science project. So first things first, you want to import TensorFlow. So import TensorFlow as TF and import Keras. And we're going to be grabbing TensorFlow's version. Now, in terms of just some classic data science imports, you've probably seen this in just your work with machine learning in the past, but we'll be importing NumPy and Pandas just to kind of pre-process some of our data, and a really, really handy library called NLTK, or the Natural Language Toolkit, which allows us to process in text data really, really easily. And then we'll dive into scikit-learn. So we'll be using just basically the splitting functions of scikit-learn in order to split up our data into train and test, just to prevent a bit of overfitting. And finally, just so we get some progress bar and some graphs, we are going to be importing TQDM, which allows us to get process bars, or like progress bars, so that it doesn't look like it's eternity. So you can see a progress bar right here, and graphs. So that's just with classic matplotlib. All right. So first things I was doing is I just simply grabbed this from the Google Drive. I loaded in the basic data and copied it to the main data path. So you'll see inside of the Google Colab kind of file storage, you'll see archive.zip, which has all of the files that we need, and specifically NER dataset reference. Then I loaded in using pandas, so pandas.read.csv. And let's go ahead and actually visualize the CSV file that we got. So effectively, we've grabbed this data from a free public Kaggle dataset. So it's completely publicly accessible. And basically, every single sentence, you'll notice that every word is annotated with a part of speech. So if you've taken a foreign language class, typically this is one of the first lessons that they teach you, is like what type of word is each of the words inside of a sentence. Or we're going to be training a machine learning model to do this for us. So you'll notice that each of the words inside of each sentence, let's just say thousands of demonstrators have marched, it will have a different part of speech for each of them. So just with some basic kind of a Python algorithm in order to load in all the data, what I've done here is I've essentially just grabbed out whatever the ground truth was, which was the part of speech tag that we needed. So in total, I think there is 32. And I've also extracted out what the specific word was too. So this is kind of like the X to Y and whatever sentence number that we specifically needed. So through processing it, just making sure that every start of the sentence, which is annotated with, if you haven't noticed inside of the CSV file, which is annotated with a new kind of like sentence one tag inside of the sentence number field, essentially that'll tell you when a new sentence needs to be made. And I've just split it up by words. So after 2 minutes of processing each of these examples, you can find them all inside of the variables I've created in this case. So I'm going to just load them all in, and then we're going to take this kind of rough data and we're going to process it down slowly using these data science libraries. Okay, so right away, before even doing anything, the first thing you want to make sure you do is you split the data. Just make sure that you're not overfitting. So you have to make sure that you're splitting the data. In this case, we're just going to do, to keep it simple, a 90-10 split between train and test. So by using scikit-learn's shuffle split function, we're going to basically just split it out 90 to 10, and we're going to be just grabbing out train X and train Y. Then, in terms of tokenizing our data, which involves taking our raw words and processing it into numbers, as machines love numbers compared to like just working with basic text, we're going to be using a tokenizer in this case. So what a tokenizer is essentially it is a function inside of TensorFlow or a specific object that they give you that allows you to take in this case, raw text and process it into numbers. And for anybody who's wondering in terms of archive.zip, that is loaded on my Google Drive right now, but it is all publicly accessible, and I will post a Kaggle dataset link to where you can download it. The reason is just because to reduce the pain of dealing with Kaggle APIs live during a workshop, I didn't want to load in all the Kaggle details right away, like just live during the workshop, but I'll send the link after the end of my portion to where you can access all this data publicly. So it's all publicly accessible. Then after using, in this case, our tokenizer, we're going to fit it on our train X and go ahead and process in each of these words. So you'll notice that word index is basically a map from every single word to a given index. And we're going to tokenize each of these words one by one, removing all punctuation to make it more clean. And any word that doesn't exist inside of our current vocabulary, which is limited to 35,000 words, just to make it a little bit easier on the computer, is going to be given just a rough out of vocabulary token, which basically just says, hey, this word was too unique. We're not going to, in this case, this word was way too unique. We're not going to go ahead and use this for now. We're going to just replace it with an out of vocabulary token. Okay, so after processing each of these words, the progress bars will fill, and we'll have all of our tokenized sequences. And so if you want to take a look at them, you will see train tokenized sentences. And you'll see each of these sentences have been transformed from a series of words to just their respective numbers. And you can actually go ahead and decode them. Let's just say I grab one sentence. I can go ahead and actually decode what the original result was. So I can just say tokenizer.decode in this case. And I can go ahead and decode whatever I had before. So let me just double check what it was called. But basically, you can just essentially just decode whatever existed before. Let me just double check the exact function name, and I'll get back to you on that. So for anybody who didn't know, you can look at all the different methods that exist by using, in this case, you can leverage dir to figure out whatever methods exist. And so in our case, what I've done is I've grabbed all the word indexes, so I can actually go ahead and decode these one by one. It might take a little bit more code. You'd have to reverse the dictionary and look up each of these words one by one, but I'll do that at the end, basically just showing off what the raw data was. But effectively what we've taken is we've grabbed whatever our data was, so train X. So this is just a series of words, right? And we've turned that all into a mapping of numbers, something that's a little bit more suited for the computer. We're doing the exact same thing, but for the Y values. So in this case, we have all these different parts of speech, right? We have maybe 32 different kinds of tags. We're going to do the exact same thing just because, again, computers really, really hate working with text. They'd rather work with numbers. And so we can translate that using a tokenizer. So we're going to go ahead and grab something called a Y tokenizer, and we're just going to fit it on all of our train data to make sure that we can just map every single part of speech token to a given index. So we're going to process it in the exact same way. So you'll notice the code is literally the same. So finally, we're just going to remove any inconsistent data to make sure that everything is processed perfectly. And we'll have about 1 million examples at the end to work with. So now that we have everything basically just standardized, everything is all inconsistent examples are removed, we're going to just finally just say, we're going to pad it all. So we're going to make sure that it is all a uniform length, because computers don't like working with variable size lengths just because it's harder to run all at once. Obviously, running 32 examples at once is a lot faster than just pushing one example at a time. And so by padding all our sequences or truncating, making sure that every single sentence is 30 length max, we're going to just train this model a lot faster. So we can just leverage tf.keras.preprocessing.sequence.pad sequence in order to make sure that everything is of the same length. So now let's go on ahead and train our LSTM. So just like how Gagan was explaining before, we can go ahead and actually create an LSTM, or we can create an entire TensorFlow model using just a list. And this is by leveraging our keras.sequential module. And so we can just basically, from this Python list, I can isolate it a bit. It is warning me that I'm not using my GPU because I haven't started training yet. But basically, just from this Python list of layers, I can actually create an entire neural network that is customized to my liking. So in particular, what I've done is I've used an embedding layer, which says, given our indices, let's just say the numbers like maybe 13, 24, etc., I'm going to grab out a vector that represents its meanings. And so what an embedding layer does is, rather than forcing the computer to memorize 35,000 different words, but just based on one number, which is hard for any human, and it's also hard for computers, we're going to say that each of these kind of numbers, like let's just say the number 0, gets turned into a vector of length x, and it points in some direction. So if you've taken vectors inside of high school, it'll point in some direction with some magnitude and direction. And so we are going to do the exact same thing, but for every single word. And words that point in the similar direction with a similar magnitude and direction will be similar in meaning. Meaning that, let's just say I have an arrow and it's pointing to the top left. That might represent the word dog. And the number, or I guess the word canine, would be pointing in a very, very similar direction because they're closely related. While a word like chair might be in a complete opposite direction. And so by doing that, we can represent meaning inside of the words by a value of numbers, compared to just saying, hey, computer, memorize 35,000 different words. Have fun. So in our case, I'm going to say that each of our vectors are going to be 64 dimensions, just to give it a little bit of leeway. So every single word can be mapped into this 64-dimensional vector. And this is thrown into two LSTM models, just going back to what I was talking about before with the bidirectional one, where it can process both left to right and right to left. And we're just going to say that in every single layer, we're going to grab an LSTM. We're going to process it with 32, so 32 dimensions, and we're going to return as sequences, meaning that rather than collapsing everything into one vector at the end, which means that we can no longer run another LSTM out and we only get one output for the entire sentence, which doesn't exactly make sense for named entity recognition, we're going to return every single word back just to make sure that for every single word, we can get a classification result. We're going to do this twice just to give the model a bit more power, kind of just stacking the layers, kind of the premise of deep learning by stacking layers together. And then we finally say keras.layers.dense, which basically just takes every single one of our outputs and processes in them one, basically just saying this word gets processed with a dense layer using the time distributed layer. So Gagan explained that a little bit before, but time distributed just says for every single word, run the same operation on it to get a classification result on every word. So every word will now have what part of speech does it represent. So one really powerful thing is that after you've built your model and you've decided that you're happy with it, you can actually call something called model.summary, which basically just says, okay, given our current model, I want a summary of every single layer. So my embedding layer, my bidirectional layer, and in this case, it would be two bidirectional layers stacked on top of each other, and a dense layer at the end to say, this is our classification results. And in the end, we have 1.7 million parameters. So that sounds like a lot, but I'm almost 100% sure that Gagan's transformer model will be a lot larger. So this is kind of just scratching the surface with deep learning, 1.7 million parameters. You can definitely go a lot deeper, a lot larger with parameters, because deep learning is all based on those deep layers with millions or billions of parameters. So pretty simple model, just an embedding layer with a bunch of different LSTM layers stacked on top. And then finally, we're going to use model.compile, which allows us to basically just say, basically the idea is that we're going to take, in this case, model.compile, which just says, given our model, we're going to give it an optimizer, in this case, Atom, which is just a classic optimizer that we're using. And we're going to, sorry, I see a few questions in the chat. Sorry. Okay. Yes. So I will send you all of the okay, yes. So in terms of all of this code that I was talking about before, it needs an authorization code and all that like archive.zip stuff. After I'm done with all of this, while the model's training, I will go ahead and send you guys all of the data that I use. So I stored it on Google Drive, which is why there's an authentication step. Um, you guys can download it directly from Kaggle and upload it just via Colab's interface. The reason why I didn't want to do that is just the risk of technical errors. Google Drive's a lot more reliable than, let's just say, Kaggle's API in case that went down or something. So I just use Google Drive. But I will send you guys the Kaggle link, which is a popular data science platform, and it has the data set. So I'll send you guys that publicly accessible link, and you guys can just press download zip. Okay? Is there any other questions? Hard drive. And you open up, yes. So I will send you guys that in like maybe 5 or 6 minutes. I'm just going to go ahead and explain the training, and then I'll send you guys all the resources. And I might even here I'll also show you guys how you go about downloading inside of inside of Kaggle, just to make this a bit easier. Okay. So next, I'm going to go ahead and compile this with an optimizer. So we're going to explain that a little bit before, but optimizers is how we go about actually training the model, how we go about like improving it. And so in this case, we're going to grab, let's just say, our bad guess, and we're going to slowly improve it. And Atom's just the classic one that we always use. So if you're worried about which optimizer to use, Atom's pretty much the safe bet. But obviously there might be a bit better if you're tuning in a bit more. But just as a safe bet, just start with Atom. And then we're going to be using as our loss function, it's called categorical cross entropy, which basically just means given our distribution, let's just say there's 32 different kinds of parts of speech tags that we're going to be using. For every single one, we want to push the probability, like the output layer, the probability that a given, like the answer is the highest probability of our model output. So if it's lower, we're going to punish the model more. And Atom is going to do its absolute best to make sure that the correct word is going to be pushed to 100%, while the rest are going to be pushed down to 0. So kind of just slowly improving on the actual like confidence of the model, and we punish it based on how unconfident it is in the given word. And finally, we just say as a metric, we say accuracy or AC, basically just saying if we just take pure accuracy, which isn't actually the best metric, you might want to use something like F1 or F beta or something like that, just any other score. But just for simplicity, we'll use accuracy. How spot on is the model when I just basically round everything up and down? So after compiling it, you'll notice that everything is now ready. It won't actually give you any messages or anything. And then we can go ahead and actually form our TF data sets. So basically, in order to create this data set, the easiest way is from the NumPy arrays that we already have, right? The NumPy arrays that I created up above. So in this case, it would be padded train X. You'll notice that they're all NumPy arrays. You can actually create a TensorFlow data set. Gagan touched on this before, but you can basically create a TensorFlow data set from these tensor slices. And so by using tf.data.dataset from tensor slices, we can go on ahead and process all this data in just using that module. And so it allows us to create a TF data set with really no struggle whatsoever. And so we're going to do the same with train X, train Y, test X, and test Y. And then we're going to just zip them together, meaning that for every X, there's going to be a Y. We're going to try to find out that relationship. So it's basically just we're training a very, very overly complex function to map from X to Y. So we can leverage that kind of function in the end for our downstream tasks. So for instance, if I want to deploy this model for my hackathon project, I would just use my black box function it's basically my deep learning model. You want to treat it like a function where there's just basically a black box. I give my X, I get a Y. That's kind of the idea. So I want to map every single one of my X values to a given Y for me to learn. And some of this is just to make it faster. This code down here is really just to prefetch some stuff. It's basically just saying shuffle the train data set give it a batch size of 32 so we can run 32 examples all at once instead of running it one by one. And then we're going to just prefetch. So while one is processing, I'm already going to grab the next one just out of the buffer just to make sure it's as fast as possible. And so that's one of the really benefits of TensorFlow is that there is that kind of ability to customize and make it a lot faster. So PyTorch is around the same speed, but it's a little bit slower just because it doesn't have those nitty gritty kind of optimization details that TensorFlow might provide natively. And so finally, after running this and we have our TensorFlow datasets, we can actually go ahead and take a look at them using train dataset and test dataset. And it actually just gives you all the information. It says, okay, every single one of my x's are going to be a list of 30 words. And same for the y, because every single one of them is going to be mapped to, every word inside that sentence is going to be mapped to a part of speech token. And both of them are integers because they're just tokens for now. And so you'll see that test and train are both the same. And we're ready to actually just go about training our models. So always just make sure to do those sanity checks to check that your data is not the problem. You won't believe how many times my project have messed up just because there's like a tiny mistake in the data that I just didn't bother catching because I was like, oh, it's probably fine. Just make sure to always do those sanity checks before you go about training, because a lot of the time, if you have bad data, it's the classic saying, garbage in, garbage out. If you have bad data, your model will never be good. Okay, so let's go ahead and train this. And it'll actually take a bit of time. So in the meanwhile, I will show you guys the Kaggle platform and where you can specifically find it. And then I'll hand it over to Gagan, who can explain his Gagan, who will go ahead and explain the TensorFlow. I guess it would be the transformers portion. So let me just go ahead and just change over to the Kaggle platform, and you can go ahead and download. And I'll show you how to download the data set.
Hey, so now we're actually going to be focusing on how to use transformers. So all the models that like all the libraries that Andrew was talking about are some of them are partially already been downloaded to Colab, but the libraries that we're using here, like which are basically data sets, transformers, and SQL, are not do not come with Colab because they are a bit heavy libraries. So we just be downloading them from we just be using pip install for them. And as we can see, I've already done the cell, so it has already been downloaded. And then the next thing that we need to do is we need to log in into the Hugging Face CLI system. And so just to do that, so we just need to do Hugging Face CLI login. And once we do that, we'll be prompted for a username and a password. So my username is Gagan3012, and I've already entered my password. So you guys can go ahead and you can run the same one to get the same results as well. And so this is pretty easy. So now the one of the major differences in what Andrew was doing with TensorFlow and what I'll be doing here is that I will be using the data set that has already been using the dataset library. So this notebook, so you can actually reproduce it without having to download the dataset on your own. So all you need to do is you just need to import the dataset function and then download the dataset from just by giving the dataset name. So once we run this function, we can see that the dataset is going to be downloaded. So it takes a while because it's not a very big data set, but it still takes a while for the data set to get downloaded. So as we can see, the data set dict is being downloaded. So it features train, validation, and test data sets. And now let's actually go ahead and start processing the data. So here I'll be using the distal word base uncased model here. So if you would want to actually check out the distal base model, you can also check it out here. It is one of the most downloaded models on the Hugging Face Hub. And now as we can see, so I'll be using three epochs, but maybe to simplify one, I will just be using one epoch here. I mean with a batch size of 16. And then we also have, and just using the dataset library, we can also use the dataset. So now since you already downloaded, let's actually go ahead and now let's tokenize the dataset. So firstly, we download the tokenizer, which is just using an auto tokenizer here. Since it's a simple BERT model, we just using the same auto tokenizer here. Now, once the tokenizer is being downloaded, so as we can see that all of the tokenizer files are being downloaded here, and always be sure to use like the GPU instance here, because otherwise your training might take way too long. And now let's actually go ahead and start tokenizing the data set. So before we actually go ahead and we tokenize the entire data set, let me show you guys how does the tokenization actually work. So for tokenization, we actually see that firstly we just have a data set here. So I'm just going to use the first first row of the data set and see. So now that we actually see the first row data set is just EU rejects German called boycott British lamb again, which is a normal sentence that we have here. But once we tokenize it, it's all in lowercase. It's all, and we also added the different. We have also added the different separations here as well. And now let's actually go ahead and maybe just align the words and make sure that everything is in order as well. So now we just align. So now everything that I've done here, we need to combine this into one function and run datasets.nav as well. So now we're just going to be going ahead and we just need to tokenize and align all of the tables here. And so now that we've aligned and tokenized all the labels, we just need to apply it and map it to the entire data set. So now, and before we actually do that, let's actually take a look at what the different entities that we have here are. So firstly, we have O, and O basically means that it has not been identified. Then we have B person, or which is a person has been identified. A person has been identified, the one which is at the first end, which is the first token of a person. And I person is which is the second part, which is the second or the end part of the person. And similarly, we have organization, we have location, and we have miscellaneous. So let's map our entire data set and let's apply the same function to our entire data set. And we have done it for train, test, and validation data sets as well. And now let's go ahead. Since we are using Distilbert as our base, so now let's go ahead and fine tune the model to get a better model out of it. I've already explained what pre-train and fine tuning of a model is, and so I think you can always go ahead and refer to that. So now that we're actually going to be downloading the model, it's really important to pay attention if you want to actually just take a look at what the different layers of the models are. And it just takes a while. So the model is not a really big model; it's just 268 MB, but it just takes a while for it to be downloaded. And now do we also do get a few of these warnings, and I've already added. So if you just go into the notebook, you can already always go and see what the details are and why the warnings have been coming. And if you just want to maybe read more into it, I will not be explaining why all these things. You can always go ahead and take a look there as well. But now let's go ahead and define our training arguments. So firstly, we just want to define our folder to be test and yarn. And then we also need to define our learning rate, our evaluation strategy, our per device eval, batch size, our num training pods, weight decay, and whether we want to push it to hub or not, and with what name do we want to push it to the hub. So let's go ahead and also define our training arguments. Just so you know, I'm not actually using TensorFlow or PyTorch here. Like all the compute that is being done here is using a PyTorch backend. But here I'm just using the Transformers API, which makes it extremely easy to for fine tune it for any task here. All right, now that we are ready for actually our training, we just need to collate our data and make sure that our tokenizer is actually working well and for token classification tasks. Again, I've already added all the clues and all the details. Why do we need like a data collator? And so you can always go ahead and revisit our file as well. But finally, let's actually go ahead and test out our metric, and then we can also download a metric. So here we will be using sequence eval, or which comes in the form of SQL package using load metric. And let's go ahead. So I've already written a function here which will calculate the precision, recall, F1, and accuracy of all of these different things. And finally, we come to the trainer part. So in trainer, we define a model. We define the training arguments. We define the train data set, eval data set, the tokenizer, and the compute metrics method. And now that we've defined the trainer, all we need to do to fine tune our model is that we just need to call trainer.train dataset. So the first thing this will actually do is this is actually going to create a data set. So if I go to my profile on the Hugging Face Hub, you can see that I do have multiple models here. So what this is actually going to do is this is going to actually this is actually going to create a Distilbert based uncase model into an empty directory. So now this is so I've already ran this file before, and you can also see that I've already done this before as well. So we already do have a model which has been pre-trained before. So we're actually going to be use a pre-trained model along with that, and we'll be using that same model to fine tune it again and again. So we wait, and then the next step would be just to just train the model, and just by using trainer.train. And once we actually done training model, we just be going ahead. So let me just run the train file. Once it's done downloading the model again, we just need to evaluate the model and see how good it's performing. Let's go ahead and evaluate the model as well. And finally, if you want to predict and get all the particular predictions for each of them, we can do that as well. And now that we already downloaded the data set, it's just gonna take a few seconds before we can actually use it and start training as well. In the meanwhile, are there any questions that I can help answer, or anything that about the transformers library, or any of the code that we'll be working here with? Andrew, do you want to jump in right now, and maybe you can take over and explain a few of
Yeah.
those things?
So before I'm going to show both the LSTM results and kind of analyze it, but before that, just to show you guys how you would actually go about using the Kaggle platform. If you take a look at my screen right now, you will notice that I am on the Kaggle platform that I've linked inside the chat. Basically, I am already signed into my account, and specifically mine right now. But the idea is that you'll load in just a page similar to this. You might have to create an account, but all the data, if you actually look, is all on this platform. So you'll see the exact same data that I was using is inside of here. And once you've signed into your account, you can just simply press the download button. And so it will just download that archive.zip file onto your local computer. And so when you actually go onto your, let's just say after it's done downloading, it's 3.2 megabytes, so it's not too large. It's just, I didn't want any technical difficulties. Once that's done downloading, all you have to go about doing is you would go onto your Google Colab link. Let me just go ahead and share that. So compared to just running the Google Drive link, you'd go into Google Colab, and they have a really nice drag and drop interface. So you can literally just drop the file. In this case, it's the file that I downloaded from Kaggle. It's called archive.zip. And you can just drag and drop it right into the file section. And in this case, you can just start running code cells directly from here. So from this fourth cell, you just run cell 2 in this case for TensorFlow, and you would run the unzip file, and then everything else should be good. Okay? So that's how we gain access to the data. Specifically, it's all public domain. Specifically for my LSTM training, you'll notice something that's really nice about Keras and Model.fit specifically is that they will also give you automatic progress bars. So in this case, the data actually isn't too large. 1 million examples for text isn't actually that problematic. And so it all trained within a few minutes. But typically the longest that I typically train models for epoch is maybe like an hour or two per epoch. And so just having that that kind of progress bar to kind of slowly track your progress like as it's training, it's a really nice sanity check just to make sure that after like the hour that you spent training on epoch, you can at least see that your model's slowly improving throughout the process. And so while you actually go about training the model, these values will automatically update. And you can see first they'll have a training phase. So on, let's just say it was like about a million examples. So it's about 1200 times our batch size. And then you have your testing phase, which is 144 times our batch size. And this is just how we get our metrics. And you'll notice that slowly as we train more and more and more, you'll notice that the model is getting better and better and better. Accuracy is improving while loss is decreasing. And that's what we want to see. And by the end of it, I've only trained it for 10 epochs, but in theory, you could train it for a lot longer. By the end of it, you will see that I've collected all the data inside of a loss list. So you'll see all of the losses as epochs go on. And you can see something inside of accuracy on how accuracy is improving slowly as the model is being trained. So 62 up to 74, 79, 90, 94, and it converges all the way up to 94.5. And so this is on the test data set, by the way. So this is on us evaluating on the test data set. So it's actually doing a pretty good job at not overfitting. And so after doing all this, I can actually go ahead and actually plot my training data, which is probably the most valuable thing you can do with it after you're done training. Just to do a quick visualization, you'll just use matplotlib and plt.plot to kind of visualize. And you want to see these kinds of smooth curves going down. you'll see that it's slowly starting to converge. So as the loss is getting better and better and better, so it's decreasing, you'll notice that it becomes a little bit more unstable at the bottom, just because obviously it can't always just keep improving until it gets into like the negative range. It will slowly plateau, and so you'll notice that the start of it is happening. However, you could definitely train it for a lot longer. You can see that it hasn't really plateaued too much. And in terms of the accuracy, you can see a slight more of a plateau, but it's still rising at a pretty decent rate. And so in theory, you should maybe train that for maybe double the time, like 20 epochs. But you can see some really good progress from my LSTM model. Now, you can definitely boost this score using the transformers library, just because all of that data that Google has trained already on their past corpuses and like corpi, and like basically just training all those data, like pre-training their models on BERT and stuff like that. And now you can leverage all that power, all those powerful models on NER. You can definitely achieve a lot better results. So in this case, 95% is actually mediocre. You can definitely reach around 99, maybe even like close to 100% accuracy with the really powerful BERT model. But just for a simple demonstration, I would definitely recommend starting off always simple. Make sure that you just have a baseline to just double check that your data is fine. Just because remember, garbage in, garbage out. If you have bad data, you will have a bad model, no matter how good, how powerful your BERT model is. And so, how do you do the drag and drop? Um, you would just so do you see like the file tab? You would like press that, it opens up your file system, and whenever you download something, I don't know if it's the same on like Chrome, but it's at the bottom. But you can just grab like in Finder, like Windows or wherever you download it on your local computer. You can just drag the file directly in, and it'll say something like drop files to upload them to session storage. If you just let go, you'll see that there's like a progress bar at the bottom. Like if you just drag and drop it, you'll see that there's like a progress bar at the bottom saying that's slowly being uploaded. So if you just press this file system, you grab whatever was downloaded to your local computer, you can drag and drop it, and then you can start working with the data. But in terms of what's it called? Back on track. In terms of just improving models, obviously using larger and larger models will bring better performance. The only warning is that it will take a lot longer to train. The reason why I kept it so simple with like a 32-dimensional LSTM is just so it could train in these 2 minutes. So Gagan's model is likely going to take a bit longer, but it will be more powerful. So hopefully, as I've analyzed a bit, I'm going to introduce one last concept, and hopefully by then, Gagan's model is done training. So in terms of saving models and saving weights, obviously when you're using a model for a hackathon purpose, you don't want to just see this graph and call it a day. You need to save these models so you can maybe deploy it to a web application or a mobile application. And by the way, TensorFlow has some really good it has a really good API for both mobile and web development. If you want to deploy your TensorFlow model to the web, I would recommend using TensorFlow.js, which allows you to basically just stick a TensorFlow model onto JavaScript directly. In terms of deploying to a mobile application, there is something called TensorFlow.lite, which allows you to take your TensorFlow model that you've already trained and send it to your mobile application where it will run a bit faster, so that maybe low-power devices like your cell phone can still run these powerful models. And so those are just two APIs you might want to look into, especially as we're approaching Hack the North. And yeah, so in terms of just saving base weights for maybe just like a Kaggle competition, or you just want to load it back onto a regular computer again, you can use model.save. This will load everything onto a file called model.h5. And you'll notice that it is like a 20 megabyte file. So it's not too large at all. But it basically stores everything about the model, including the structure, all the weights, and you can just directly load that in. In terms of loading in, let's just say weights specifically. So this is what you can do with PyTorch, and PyTorch doesn't actually have the option to save an entire model. If you just want to save the weights, to save a bit of memory, you can go ahead and use model.save weights, which will only save the specific numbers that we need. And so the only issue with that is that when you have to go about loading it in again, just make sure that you create the exact same model and use model.load weights. So that'll allow you to load in all of that back into your TensorFlow model and restore the progress, but it's definitely more error prone. So if you have the memory, you might as well use model.save, but there are certain situations, like if you're using a inherited model, but you might dive into that a little bit more in the future in terms of just more complicated TensorFlow models. If you're using a subclass model by creating like object-oriented programming, and you're using like subclass layers, like using like tf.keras.layer and stuff like that, which was introduced a bit before, you won't be able to actually save using the canonical method of model.save, you'll only be able to save the weights. So just keep that in mind. You'll have to recreate your model completely the same and load it back in using model.loadWeights. Okay? So hopefully by now, Gagan's model is training, so I'll pass that back to him.
So yeah, now we can actually see like the training is actually completed, and we've trained for 3 pouches, and our accuracy is 98.3%, which is very good. And one of the biggest advantages that we also evaluated it and we got like the different laws. And so one of the biggest advantages is that we can also test it instead of actually using. So we already uploaded it to the Hugging Face Hub. Now instead of testing it on a local system, we can always go ahead and test it on the hosted inference API by Hugging Face. So that allows us to just report. So we suppose we have like a demo sentence here, like my name is Khan, I live in Berkeley, California. We can just go ahead and just run the commute. So this actually saves us a lot of time and a lot of money as well, because these compute can be pretty expensive. So that's why it's always better to use the Hugging Face Hub and the Hugging Face API as well. And it just takes a while for the model to be loaded. And once the model is done loading, we can just go ahead and we just see the results. And that is basically how we can actually just go ahead and evaluate our models. And one of the really good things is that all of our metrics that we reported have also been added here. So all the time and all these details have also been added here. And here, and finally, as we can see here, we can see label one, you can and Berkeley. So if we go back to see what label one and stuff were, and they're in the same order here. So we can see like the label one would be B person, and label five would just be B law, which is Berkeley, California, which is pretty accurate here in this case. And finally, we do have all these resources here. So for resources for TensorFlow, find resource for TensorFlow and for Hugging Face in this page, and you can get all the details of the workshop as well. And thanks so much, everyone. Thanks so much for joining us today. And it was really a pleasure to talking to and explaining all these details to all of you guys. Thank you.
Yep. So do we have any last minute questions in terms of just like, yeah, so for sure run into the feedback poll. And then if you guys have any other questions, just drop them into the hop in chat or on Slido, both work. Yeah. So please just fill out the general feedback survey. And yeah, if you have any other questions, don't hesitate to ask via Hopin or just through the Slido, and we'd be happy to answer. Yep, so in terms of adding models into Hugging Face, Gon, you might want to take that over. Yeah, just adding that model and pushing that directly to Hugging Face. I can also help if needed. Okay. Can you guys see my screen? All right. Okay, that's fine. I'll just show you guys specifically how you push to hub. So I think my screen show's disabled for now, but oh, there it is. Okay, so specifically on how we go about pushing models to Hugging Face specifically, Hugging Face is known for being very, very all-in-one. So you can actually, a lot of this is very, very simplified to make it as easy as possible for you to work with deep learning. And so in order to push the data to your hub, after you've trained it, you can legitimately just type in the code trainer.push to hub, and it will save everything under your account. So if you look under Gagan's public feedback or public like thing inside of Hugging Face, like his public profile, you will see the specific model that he has pushed, because it allows you to just push it directly under your username under the allocated storage that you have. And so just by using trainer.push to hub, all of your data about training and history and all that stuff about like running the model, it'll all automatically just be pushed to the Hugging Face library. So you can just go ahead and look on the public domain for all these different all these different models that people have trained, and you can actually use them inside of your own projects. So kind of leveraging their work and then building on top of that to build an even better system. So yeah, just using that simple line called trainer dot push to hub, you're able to actually push all that data to Hugging Face. Is there anything else? All right. If there isn't any other questions, let me just double check the Slido. Um, yeah, it was a real pleasure to be hosting this workshop. And yeah, thanks everyone for coming. Again, feel free to reach out. I'll give you guys my Discord if you need it. Yeah, if you have any other questions about TensorFlow in general, just feel free to DM me. I don't know if Egon wants to post his Discord too, but yeah, feel free to reach out to me on LinkedIn or through Discord, and I'd be happy to help you out during, like, maybe not during the hackathon because I will also be hacking, so that might be a little bit not allowed. But I'd be happy to help out in general, just about TensorFlow and syntax and stuff like that. And so yeah, just feel free to reach out through Discord or through LinkedIn, and I'd be happy to help with any technical questions or any further resources about TensorFlow. Again, we kind of brushed over the workshop slides in terms of resources, like, a little bit quick, but yeah, just check out tensorflow.org. And yeah, thanks everyone for coming. Have a great day.